All right. I'm going to start with a demo, first thing on today. Review some projectile motion. Reiterate. I have a car that rolls along. There's minimal friction, a little more than an air track, but not a whole lot. And there's a little ball. I made it a sad ball. Remember, it's really happy. Do you remember that? Yeah. Why is this really a happy ball? Do you remember? It doesn't bounce. Why does not making it bounce make it happy?
Because then it has less force on it.
Less force on it. The ball comes down with certain, right before it hits, it has a certain momentum, mv. The table is going to exert a force for a certain amount of time, apply an impulse to try to change that momentum. It can change it from mv to 0, or if it bounces, it can change it from mv to mv back up in the opposite direction. So the change is nearly twice. Thus, if the change in momentum's twice as large, the impulse, which it provided the change in momentum, is twice as large. And in order to provide that, you can adjust the time or the force, but the bottom line is this is going to end up feeling about twice as much force in order to stop it and turn it around. So yeah, things that go splat, more likely to survive. You know, every bone in your body's broken, but maybe you're still alive. Okay. So go limp. Okay. So that ball, I can cock this. And there's a little photo gate back here that when it goes through this, it blocks it and triggers the ball like this. And so it shoots straight up. And so the question to you is, what happens if I push this along, it gets to here, this will fire straight up. Where will the ball land? When I go this way, it's going to fire right at this point. That triggers and shoots straight out. Where will the ball land? Gut reaction. Who thinks it'll land behind the cart? In the cart? In front of the cart? Should we make it more challenging? Does it change the problem? No, it just makes it harder for me. Okay. Woo! Now, most of you thought that. Tell me why. I see you. I'm just hoping other people are being brave too. Yeah, you try. Because of inertia. That has to do with it. Yes. How else could you explain it? That's correct. The ball and the cart have the same momentum right before the shot. Good, good. The work up, down. Okay. Yeah, Kate. You ready? I just made it so it looked cooler. It just clears the tunnel, and then while the cart's going underneath the tunnel. That just means I had to push it fast enough so it made it through the tunnel in time. Does it matter if I go slower? Yes. Yeah, ball's moving, doesn't want to stop moving, inertia, it's got momentum, same as the cart. And more recently related to what we talked about with projectile motion, they both have a horizontal velocity to this point. They're the same horizontal velocity. That's why they had together, never mind, stop there. When this guy shoots up, he now has a vertical velocity in addition to a horizontal velocity. These are the components. If this one's large, then he'll be shot more horizontally than vertically. If this one's large, he'll be shot more vertically than horizontally. Do you follow that? This would be shot more up and out, and this would be shot more out than up. But it's, so you can think of it different ways. So as soon as he gets here, he has this velocity and this velocity, and so he ends up going at the same horizontal velocity in the air as the cart is. So they move horizontally together. This guy just happens to go up and back down meanwhile. I never get tired of that. All right, good. All right, I got more good news. On Webassign, there is a link right here. I put in the announcements. For lots of reasons, long story short, lectures are now available to you to rewatch. So if you click there, it'll take you, I'll show you in a second. That's what, thank you, Matt. You've been here the most. We owe him at IMS and Instructional Media Services. And Catherine works in our department, and she's arranged so that all this happens. Now that all the technology, the way we want it to work, here you go. You click on that link, and it takes you to a YouTube account where you can see by date each of the lectures. So, you know, you can rewatch me. Sorry. And you can download these or convert them, put them on your iPod, whatever you want to do. Here's one. Remember that? I know you can't hear the audio at the moment, but it's there for you, Brandon. You can relive it and show all your friends. But anyway, right there. So I'll leave that up. And as we get the next ones on, you can watch them. To review, I think would be the best way. You're like, oh, well, we already passed all that first test stuff. Well, what are you going to forget the most of probably by final time? The first stuff. So you can go back and rewatch it. That will help you. We hope it does. Also, if you haven't noticed yet, well, I can't see from this angle. The next homework assignment's posted. You can see its due date, February 24th. We're slated for our next test on the 27th, Monday the 27th of this month. I went ahead and let you have it be due Friday, even though the 24th we'll review. But I think this one has no essay questions, so it'll be graded instantaneously. And first thing Saturday morning, you got the answer key, so you have all weekend to review that. And friendly reminder that if you have not given the superhero paper any thought yet, feel free to start. I just don't want you guys to feel overwhelmed. That's why I gave it to you at the beginning, not to overwhelm you, but so that you have plenty of time to plan and prioritize in your busy schedules to do it. I just hate for you to have to cram it all in the week before. So a friendly reminder that if you forgot about that, and you don't like to cram, there you go. Of the superhero paper? I don't remember. So let's open it up. At the bottom, you may turn your paper in to me anytime up through Monday, April 2nd. And since I've given you all semester, don't expect too many valid excuses for late papers. So you got plenty of time. Up through April 2nd. Okay, I've been forgetting doing other things. I wanted to get to this demo. Get the climb on the table again. Those are always good demos. This is ball chain. And I'm going to pull it out of the cup and let go of it. What do you think will happen? I'm going to pull this out and let go of it. It'll fall. Right. What type of energy does it have now? Yeah, well, will that get converted into? Yeah, potential to kinetic. Very good. It's all potential here. At the bottom, most of it's kinetic. All right, here you go. Oh, that was a good one. Okay, you scientists, make good observation. What else did you notice going on? Anything seem a little weird or not as expected? Yeah, they're all attached. Ball chain, yeah. Yeah, they started coming up a little higher, and at one point it was like this high out of the cup before it started to fall. Can we explain that? You're close. As he says, as the bottom was falling faster and faster, maybe that some of that energy translated up here. Is that the gist? Yeah, you're getting onto it. You can think of this one in terms of energy or in motion. There's a couple of ways I try to explain it. Which direction does the ball chain initially want to go? Yeah, it has to come up out of the cup. So it has some inertia, momentum carrying it forward. This stuff's already falling and has some weight trying to pull it back down. Well, it kind of overshoots because of momentum. You apply a force for a time, an impulse, and it's trying to change its momentum, but it doesn't happen instantaneously. So you can one way is inertia or momentum. It kind of carries it up a little, and that works. I like the energy, and you're very close, James. What I've noticed, and I didn't expect you to notice, is as the end falls, it gets faster and faster and faster, and what type of energy does it gain? Kinetic. But at some point, it doesn't go any faster. It's connected to the stuff in here, and it kind of holds it back so that at some point it can't fall any faster. But it's not to the ground yet. It still loses potential energy as it falls, but it's not going into kinetic energy. Where does it go? Into adding the potential energy back up here, and it raises it up. So you can think of it that way. So it's falling, converting to kinetic, but at some point it doesn't go any faster because it's being held back. But it still falls. It loses potential energy down there still, but it doesn't go into kinetic. It goes into some potential up here and raises it up here. I think that's cool. Does that make sense? No? Okay. Oh. Okay. Did that. Chapter 13, liquids, if you couldn't tell. First thing, pressure. We get to learn pressure and how it relates to force. Let's move this up a little for the moment. So, where are we at? 15th. So Wednesday and Friday I'll be doing liquids. I might get to gases on Friday. Monday's a holiday. Don't come. Wednesday on the 22nd we'll finish up gases. 24 I'll finish anything I didn't get to in review on that Friday. And we'll have our next test. So counting today, we have 4 more lectures before the test. Pressure. Give it big P. And it is a force over an area. And believe it or not, if you don't know, this you already knew. You just might not have known it. It was called pressure. Pressure is measured in pascals. Which is a Newton force over square meters. My notes are wrong. And how I know you've known this is because would you rather get stepped on by somebody wearing a snowshoe or high heels? Right. All right, will you help me? Just put your hand down there. It'll work. This weighs 15 pounds. That's a force, right? I can't change its mass. Well, I'm not going to. I'm not going to cut it off or anything. It weighs 15 pounds. I'm going to put that force on her hand. Does that hurt? I don't want to hurt you. Okay. So I spread it over the area of her hand. Force over here. If I flip it this way, we have a square inch. And if I put that on her hand, use your left hand to control. You guide how much goes on it. Because if it hurts, lift back up. Let go until, can you handle that? Yeah. Which is more comfortable? Yeah, the other one. Thank you for helping me prove my point. And that's just to show force doesn't change, the weight's the same, but if you apply it over a different area, you can change the pressure that you feel. And a lot of times people say, oh, that feels, hard. And that's one where in layman's terms, are they referring to pressure or force? That hurts more. Well, it's not any heavier, but you're concentrating it all into one spot so that fewer points have to support it. That's what pressure is. Questions? So in nature, you can see it in snowcats. They have really big paws because they spread their weight over a larger area. And if you increase A, the pressure decreases. And so they're less likely to sink into snow. All right, another term we need is density. It came up earlier. It'll be a little more important now. I'll make it a big D. Mass over volume. So it would be in kilograms per cubic meter. Sometimes people refer to, if that number is too huge for the substance, they might use grams per cubic centimeter as the units for density. I made a note. Checkpoint on page 215. I must have liked it. He says, here's an easy one. When water freezes, it expands. What does this say about the density of ice compared to the density of water? Ice expands. So which one's more dense? Water, very good. Because you take ice, it has a certain mass. If you freeze it, it has the same mass. But if it expands, then the volume increases and the density decreases. So yeah, ice is less dense than water. And as we're going to see, that's why it floats. If it was more dense than water, it would sink in water. Okay, then he says, here's a slightly trickier one. Which weighs more? A liter of ice or a liter of water? Oh, we originally had most of you shouting out the same. Now some of you are... It's right here on page 215. Don't say they weigh the same, because that's incorrect, sorry. A liter. That means they have the same volume, right? Which is more dense? Water. If this is going to be a bigger number, then water has to have more mass, right? So the liter of water should weigh more than a liter of ice. Do you see that? Does it make sense? Tell me if it doesn't. If they're both 1 liter, then we're not changing this value, right? Water or ice has a bigger density? Water. If this is bigger, how do you make this bigger with the same volume? Yeah, so water has more mass, which means it's going to weigh more.
So how does that change with freezing? It's still the same product.
Yeah, if you take a liter of water and you freeze it. You have not changed the amount of mass. But water expands when it freezes, and that changed its volume. So ice now takes up more space. For that same liter of water now takes up more than a liter of volume as ice. Say again? You don't lose it. When it freezes, it's the same weight. You take that liter of water, it has a certain amount of mass. Freeze it. We haven't changed the mass, so we haven't changed the weight. But it's no longer a liter. It's bigger than a liter. It expanded. Yeah, back to the question, because we've done it various ways. This said, which weighs more? A liter of ice or a liter of water? To get a liter of ice, you have to start out with less than a liter of water. Or more and cut it, yeah. So I'm using this as an interplay just so you start thinking of this relationship and your guide to your thinking. Yes, Kate?
I may have just missed something.
That's fine.
It says, it's talking about the icebergs, and it says ice is 29 times the density of water.
Yes. She says ice, it says an iceberg and ice is 0.9 times the density of water. So if the density of water, which is 1,000 kilograms per cubic centimeter, meter, 0.9 times that gives us 900 kilograms per cubic meter. This one's water, and this is ice. That's nice. So ice's density is less than water. Yes? A liter of water, a liter of ice. Water should weigh more because it takes more mass to have a liter of water than it does to have a liter of ice. And you can review that on page 215. I was reading the checkpoint. That's why I liked it. Okay, which has the greater density? 100 kilograms of lead or 1,000 kilograms of aluminum? $100 kilograms of lead or 1,000 kilograms of aluminum? And who has the greater density? I don't know if you'll know it off the top of your head. They have a list of density table here, but I can do it qualitatively. Density is mass over volume. He chose these two. Which one's more dense? Yeah, lead's a lot more dense than most things. So he has a big D. Big D, little m. This has a smaller d, big M. How do you think the volumes are going to compare? To get a big D, we got to have a smaller volume. Pretty small. And to get a smaller D here, that's really big. Yeah, we're going to need. So you already knew lead had the greater density. You can go through this game, which is why I showed you, but there's an easier way. You already knew lead was more dense. That was the answer to the question. It doesn't matter how much mass you have. A 100 kilograms of lead compared to 1,000 kilograms of lead, both lead, they're going to have the exact same density because they're lead. Just don't want you to trip on that. What's his last one? Yeah, I don't want to do that one. Okay. So that's density. Then we get to pressure in a liquid. So that's where we usually see it. And pressure's the theme here. for the next 2 chapters. We've dealt with forces, usually solids, and we exert them over areas. Hopefully now you got a feel for what that is. But you can do the same thing with fluids. And a fluid is anything that flows. A liquid, water, blood, but also a gas, helium, air. That's the next chapter. So we're going to relate pressure and see how that changes and affects things, specifically now in liquids and gases. So you with me? If it's something's weight, and it doesn't matter whether it's a solid, a gas, or a fluid, it has mass. Air has mass. I hope I didn't have to convince you. I took that for granted. We take it for granted, but air is substance, and it does have mass. It's just very small. So it does have weight. And so does water. I'm going to write the mass. You don't have to reproduce this. But it's to get to a formula I want to show you, a relationship. If we rearrange this guy for mass, do you see how I get this? We can say mass is density times volume. Tell me if you didn't see how I did that algebraically. I'll spell it out. So over here, I'm going to replace the m with density times volume. And then I want to shift the volume over the area. Do you remember your geometry? If you have the volume of this, how would you find it? You'd take the area of the top or bottom in this case and multiply it by the height. Does that ring a bell? This is what mathematicians like to do. So that works out to be the volume divided by the area. Just leaves the height. This is what I really want you to realize. This is not given in the book. But the whole rest of the chapter uses this relationship, and that's what some of my demos are going to do. And I want you to see it comes right from this, at least once. It's still weight over area. I just wrote the weight in terms of density, and then I got it in terms of the height, changed the geometry factors because I don't want the volume. And what this tells us is the pressure of a fluid is dependent upon the density of the fluid. If you replace water with glycerin, which is a lot more dense, you're going to get more pressure if everything else is the same. It's heavier. Gravity, if you go to Jupiter, you'll change the pressure. And height. It matters how much fluid is above you. So most of you probably know when you dive down into a swimming pool, especially when you're a kid, it's probably more likely to happen. What happened to your ears? They'd pop. That's because the pressure increased as you got more and more water on top of you. The H increased. And if you replace the whole swimming pool with glycerin and went to the bottom, they might actually pop. Of course, you can't move, but that's a different story. So this is a relationship that they figured out that comes in very handy. Let's do a couple. How about this one? This is what scuba divers have to worry about all the time. I put a diaphragm on this end, so it's closed off. There's some air in here. And it's connected to the right side. Air, 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 air. And then I colored some water. It's pushing down on the water. And we have a column of water this high. It's water. We can look up its density, 1,000 kilograms per cubic meter. Gravity, 10 meters per second squared, times this height, 0.4 meters roughly. That determines what pressure is felt right here. This column of water has mass and weight, and it's exerted over an area. It's exerting a pressure right here. What's it pushing on? This side. It's open to the atmosphere. So it's feeling the same pressure on both sides. We can use this as a barometer, and we can gauge pressure. I'm going to put this side in here, and as soon as I start going down, do you see what happens to this side? This is connected to over here. It now has to support this additional pressure. The height of this water adds to what's pushing on this side, and it pushes down harder. And look how much it can hold up. This column of water on the right side. That creates more pressure down here. But it's balanced by this additional pressure here. And these are both water, same density. We're both on Earth, same acceleration due to gravity. The H's are the same. This starts moving about, because it's a little sloppy balloon, about, let's see when it starts moving. There-ish. So, to the bottom. So that distance, a little more than a big hand here. Can you see that's the difference? Can't see. Yeah. Anyway, my point is, the depth that this went down, that additional pressure, it can now hold up that same column of water over here, because they're both water. What if I replace this with mercury? Do you think this column would be taller or shorter? Shorter, because mercury is more dense. It'll be heavier on this little spot, so it doesn't need as tall a column to provide the same pressure down here. Is this making sense? I hope. Other practical applications. This one. Got 3 holes in this column. We're going to fill it up. And hopefully you guys know where the pressure is the greatest now. Well, that's exactly why the sponge is here. Okay, close enough. Well, for crying out loud. Obviously isn't my day. Okay. Twist. There we go. Should have had out these out here first. All right, I'm going to raise it up. I'll get on the other side so you can see now. I'm going to purposely remove them. They're going to come out the 3 holes. Will they come out the same? They're going to have a projectile motion here. It's going to have a horizontal velocity and gravity accelerating it down. Will they all come the same distance? Will one shoot out farther? You think the bottom will shoot out farther? And you think that because there's more pressure down there. That's absolutely true. So let's see if that works out. Yeah, it shoots out the fastest. That one made it past the hole, so there's nothing to squirt at. You can still see the bottom one as clearly. And see, as it gets closer, there's only this much. It doesn't shoot out as fast, does it? We'll see that again down here. It's shooting out. But as this height decreases, there's less and less pressure on this hole, and it doesn't shoot out as fast like it was way out here. Okay. I like that one. Here's another one. I have a reservoir leaking. In the big container. I have a valve it's closed off right now. I'm going to open up the valve right here, and it's going to allow this to flow into here. Will it come up any of these? Or just fill up down here and stop. And if it fills up these, which one will be higher? It's closed here. They're open at the tops. All four are open at the top, closed here. So when I turn the valve, this will be connected through here. This will definitely flow into here, as you see why. There's pressure down here. But will it be enough pressure to raise fluid up in here? And if so, how will the heights compare if water comes up any of them? This one will come up highest. Who wants to agree with that? Who thinks this one will come up highest? How about this one? The same? Several votes. How about none at all? Who thinks it'll explode? Okay. All right. Doesn't happen quickly, so it's not like zesty, but here it goes. And I realize this one's kind of skinny, but can you see it? Does that help? They all came up, and they're all the same level. So the sames have it. This is to emphasize that pressure is not dependent upon volume. Another reason I like to write it this way. It's only dependent on what fluid you have, the gravitational pull on it, and how much above you have. Height, how high above you it is. I have to be careful in this chapter saying amount. It doesn't matter how much. For example, this one has a lot more water above this point down here. A lot bigger volume. More mass even, because there's more of it. But that doesn't affect the pressure down here. What affects the pressure is that it's water and that it's this high above. What that means then is this one, which has very little water, but it's still that high above, the same height as this one. So this exerts the same pressure down here as this one does. All four of them exert the same pressure down here. That's why they all come up to the same height. That's an indicator. The fact that they're all at the same height tells me that they're all at the same pressure down here, trying to push it up. This one has to hold back this much water, and this one and this one. And it seems counterintuitive because, well, this is a lot more water. It weighs more. Yes, but weight isn't the only factor now, remember? We got that area in there too, and that equates to just how much above you have, the height. So that means if you build two dams and one holds back the entire Atlantic Ocean, and say it's 100 meters tall, at 100 meters down, it's holding back the whole Atlantic Ocean. And then you just have a pond, a really deep pond, that's 100 meters. Another dam holding it back from a river. At 100 meters of the dam in the pond and 100 meters at the dam of the ocean, exact same pressure at that point because they have the same depth. Okay, we're getting to salt water versus fresh water, and that does change the density. It's a good point. And the density does affect the pressure, yeah. So salt water, which is more dense. So if it was the same height, a little more dense, would be a little more pressure down there, yes. But I think it's great. So yeah, the little guy putting his finger in the hole, stopping the dam from breaking and bursting and squirting out. That theoretically can happen as long as he can exert enough pressure to withstand the pressure at that depth. And if it's, 5 feet down, that should be easy, whether it's the Atlantic Ocean behind or a little pond. It's just the depth. Now back to more along those lines with some measurements here. Let's see. I'm measurements, but you can use it as a tool like a barometer. Colored some water. This is one of those fizz keeper caps you can use to pump air into your pop after you've opened it. What's that do inside here? It's putting more and more air inside. More mass, more mass, more mass for the same volume. What happens to the density? More mass, same volume. It increases. M's on the top. You add M in the numerator. The density increases, and so does the pressure exerted on the fluid down here. And you can keep your carbon dioxide from, I want to say oozing, bubbling out of the pop. Escaping, thank you. Well, so I can use this. It's loose right now. And I open up this end. Both sides feel the pressure of air, atmospheric pressure. That's next chapter. The pressure at this point is supported by this column of water and this column of water. Notice they settle at the same heights. And it doesn't matter if the tube goes down a ways too. Notice they still settle at the same height. You can even do a little loop-de-loo thingy. Right? If you can get over it in the first place. Just don't want to spill. And it always comes to the same height. You can do it. Because the pressures are balanced. I'm going to make the pressures not balanced. Let's put the cap on. And if I start pumping more and more air in, the pressure increases at this point because it has the column of water and the air pressure. And it can support a bigger column of water over here. And so it's not changing the fact that it's water or gravity, so it increases its height. And now this column of water, the pressure exerted down here, is balancing the pressure over here due to the water and the air. Does that make sense? And if I release it without spilling, watch this. There. Goes back down. Because I just lowered the air pressure in there. All right, seal that off so we don't make a mess. All right. Archimedes principle. I'm going to start with a demo for that one. So we can start making things sink and float. Archimedes principle. We'll show you how that works before we put it on the board. All right, I'm going to hang this. Let me show you first. This is hollow. This fits right inside. It's the same volume. This is the same volume as this space. That's what I want to show you first. So I hang this from here and we can see what its weight is. It is about 3 newtons. If I hang this from the bottom, that goes up to 7 newtons. So this weighs how much? 4 newtons. See, you're balancing forces already. I'm going to fill this full of water. To the brim. And it'll start, if it overflows, it starts leaking out the hole. All right, we're level. Get rid of the excess. Okay, this is empty. All right. What will happen when I'm going to raise this up and submerge this? It's going to go into here. What will happen to the water in here? It gets displaced. So you already know this. This is going to take up space in the water and push the water, some of it, out. Watch this at the same time. I'll raise it up. We're at 7 newtons. Okay, it's in the water. Water's starting to come out. Glad I went to the bathroom. Okay, now I want it completely submerged, but not resting on the bottom. There, it's swinging, you can see. So we're not resting on the bottom. A little higher. There we go. What happened to the scale? It's about 5.5 newtons. We lost how many? Newtons. Why does it weigh less? It was 7 newtons. Where'd that 1.5 newtons? Why are we losing that? Why does the scale read?
The water
What?
is now supported by the water.
The water's helping support it. We call that a buoyant force. Buoyant force. Yes? The bottom cylinder is in the water. The water must be supporting it somehow, at least by 1.5 newtons. Yeah. It appears to be supporting it by 1.5 newtons exactly. We call that a buoyant force. Buoyant force is, one way to find it is the weight of something in air minus the weight of it in water. And you probably all know this, it's easier to carry something heavy in water, right? You feel lighter in water. Why? Because you're partially being supported by the water. A buoyant force. And if you want to know exactly what that force is, weigh something in air, weigh it in water, and the difference is that buoyant force. But watch this. We're almost done. This water got displaced out of the bottom. We weren't weighing it. How do you think the volume of this water compares to the volume of the cylinder that I submerged? They are the same. If you want to find the volume of something, put it in a thing and see how much the water displaces. This displaces exact same amount of water, volume, as the thing that's underwater that got submerged. So, how much does this water weigh? If I pour it back in here, it should take up the same space, right? If this is the same volume as the cylinder, it should fill this up. I'll do that. Yep. And look what happened to the scale. The weight of that water, put it right back to 7 newtons. Archimedes' principle is, and we'll revisit this next time, says the buoyant force is equal to the weight of the displaced water. You put something in water and it'll displace a certain amount of water, right? If you could weigh that displaced water, that's the buoyant force. That's Archimedes' principle, the weight of the displaced water. The book explains it, and we'll review it again next time. See ya.